Hey guys, thanks for tuning in. I'm Shakti, and today we're going to be going over everything in AP Chem Unit 1. So if you want to skip to a specific topic, the timestamps for each topic should be on screen right now. And without further ado, let's get going. Okay, so first off, we're going to start off by reviewing all the different characteristics of the periodic table, which gives you just about every element that you need to know in a nice, neat little chart. Elements can be classified into groups, which you can think of as columns on the periodic table. The main groups are the alkali metals in the first group, the alkali earth metals in the second group, the transition metals, which are this big block of metals in the center, the halogens, which are the highly reactive second to last group, and the noble gases, which is the last, largely non-reactive group. You can find the number of valence electrons each group has by counting the order of the columns, skipping the block of transition metals in the middle. This is because transition metals tend to have different numbers of valence electrons from each other, with no discernible pattern between them. You're probably wondering, what are valence electrons and why do we care about them? Well, each atom on the periodic table has positively charged protons and neutrally charged neutrons in its nucleus, which is the center of the atom. Surrounding the nucleus is a cloud of electrons, which are negatively charged and placed into shells, which orbit the nucleus. Valence electrons are on the outermost shell of an atom, and they basically determine how an atom reacts with other elements. Because elements in the same group have the same number of valence electrons, they typically react the same and have similar chemical properties. For example, chlorine and bromine are both in the same group in the periodic table, the halogens. We know that halogens have 7 valence electrons. In order for atoms to become stable, they usually either have to have 8 valence electrons or no valence electrons in their outermost shell. Since chlorine and bromine each have 7 valence electrons, it's much easier for them to add 1 electron to their outermost shell, giving them 8 valence electrons, than it is to remove all 7 valence electrons. Because of this, in both NaCl and NaBr, two compounds with sodium and either chlorine or bromine, chlorine and bromine are each going to grab an electron from Na, giving them a -1 charge and forming a 1-to-1 ratio with Na. Okay, so now that we've gone over how different groups have similar properties, let's go over another property of the periodic table, which is average atomic mass. This is the average mass of 1 mole of an element in grams. It can also be called molar mass. A mole represents 6.02 times 10 to the power of 23 molecules of a particular element or compound, and it's used by chemists as a standard way to convert between different units such as grams, liters, etc. And is also a convenient way to count the different amount of molecules in something without having to count each individual one. Hey Steve, could you measure out some potassium carbonate for this lab? Yeah, just give me a second and then I'll get it.
One eternity later.
Hey man, I got the K2CO3 you asked for. Wait, how much K2CO3 did you get? Yeah, low-key, I don't know. I think I counted 1.505 times 10 to the power of 23 molecules or something like that. Wait, what did you say? So did I stutter or Wait, let me get this straight. You individually counted 1.505 times 10 to the power of 23 molecules? I mean, basically. Well, what the heck am I supposed to do with that number, Steve? I mean, I don't know. You're the one who asked for it. Do you know how inconvenient it's going to be for me to count out how much product I'm going to get with 1.505 times 10 to the power of 23 molecules? This is why no one likes you, Steve. You just make things so much harder than they need to be. Why could... Fine, bro. I'll convert to moles. Now, back to atomic mass. The average atomic mass for each element can usually be found at the bottom of its box on the periodic table. It's usually the number with some sort of decimal place after it. As we go down the periodic table, you'll notice that the atoms tend to have more protons in the nucleus, as shown by their growing atomic number. Because of this, atoms tend to get heavier as you go down the periodic table, so their atomic mass increases. You can also use the average atomic mass to convert between grams and moles, since the average atomic mass is the mass of 1 mole of a substance. If you're given the amount of grams of a substance, divide by the average atomic mass to get the number of moles. So let's say that you had 266.91 grams of copper and you need to find out how many moles of copper that is. Looking at the periodic table, the average atomic mass of copper is about 63.55 grams. This means that there are 63.55 grams of copper for every mole of copper. So you could take 266.91 and divide it by 63.55 to find out that there are 4.2 moles of copper in 266.91 grams of copper. But what if a problem gives you the amount of moles of a substance and asks you to convert to grams?
In that case, you'd multiply the number of moles of the substance by its molar mass in order to get the number of grams.
If you had 23 moles of bromine, you could multiply 23 by 79.9, which is bromine's molar mass, and get 1,837.7 grams of bromine. So, 23 moles of bromine is 1,837.7 grams of bromine. The exam could also ask you to find the molar mass of compounds to use for calculations.
To find the molar mass of a compound, find the molar mass of their individual elements, multiply them by their subscripts, and then add them together.
For example, to find the molar mass of magnesium sulfate, which is MgSO4, you first need to find the molar mass of magnesium, sulfur, and oxygen. Looking on the periodic table, you'll find that the molar mass of magnesium is 24.3 grams. The molar mass of sulfur is 32.06 grams. And the molar mass of oxygen is 16 grams. In 1 mole of magnesium sulfate, you have 4 moles of oxygen. So we take the molar mass of oxygen and multiply it by 4. 4 times 16 equals 64 grams of oxygen. And there's 1 mole of magnesium and sulfur and MgSO4, so we don't have to multiply their molar masses by anything. Now that we have the molar masses of all the different elements in the correct ratios, we can add them together. 24.3 grams of magnesium plus 32.06 grams of sulfur plus 64 grams of oxygen equals 120.36 grams of magnesium sulfate. So, 1 mole of magnesium sulfate is equal to 120.36 grams of magnesium sulfate. We can now use this number to convert between moles and grams, just like we did with the last 2 problems. It's important to note that some problems will occasionally make you convert between units like kilograms and grams. 1 kilogram is equal to 1,000 grams. So, if you're given the value of something in kilograms and to convert to grams, you would multiply that value by 1,000. Likewise, if you're given the value of something in grams and you need to convert to kilograms, you need to divide that value by 1,000. This type of conversion is going to happen with a lot of different units in this course, especially when we get to units like joules and other things like that.
Additionally, if the psychos that write the AP test need you to find how many individual molecules are in a substance, for whatever reason, first, convert your given amount into moles, and then multiply it by 6.02 times 10 to the power of 23. This is because there are 6.02 times 10 to the power of 23 molecules of a substance in a mole.
So now that we know about moles and molar mass, we can start learning about how to calculate empirical and molecular formulas.
A molecular formula gives you the exact number of different atoms that are in a single molecule of a substance.
For example, the molecular formula of glucose is C6H12O6. That tells us that in every molecule of glucose, there are 6 molecules of carbon, 12 molecules of hydrogen, and 8 molecules of oxygen. An empirical formula gives you the lowest whole number ratio of the different atoms in a molecule. Glucose's empirical formula is CH2O. This is the lowest ratio of the different atoms in glucose, and it tells us that for every atom of carbon or oxygen in glucose, there's 2 atoms of hydrogen.
You can also convert the molecular formula to the empirical formula by simplifying it into a whole number ratio if you can.
In C6H12O6, you can divide carbon, hydrogen, and oxygen subscripts by 6 to give you a 1:1 ratio of carbon, hydrogen, and oxygen atoms.
You can also find the molecular formula for a substance if you're given the mass percentages of a substance, or if you're given the amount of grams of a substance's different elements.
Let's do an example so you understand what I'm talking about. This problem says an unknown compound is 43.4% sodium, 45.3% oxygen, and 11.3% carbon. And it asks us to find the compound's empirical formula. When we're given percentages, to find the empirical formula, we first want to assume that we have a 100-gram sample of this compound. If we have 100-gram samples of this unknown compound, we can multiply the 100 grams by these percentages to find out how many grams of each atom we actually have. So we have 43.4 grams of sodium, 45.3 grams of oxygen, and 11.3 grams of carbon. Now that we have these masses, we're going to divide each of these masses by the molar mass of the compound to get the number of moles. 43.4 grams of sodium divided by its molar mass, 22.9, gives us roughly 1.89 moles of sodium. 45.3 grams of oxygen divided by its molar mass, 16 grams, gives us roughly 2.83 moles of oxygen. And finally, 11.3 grams of carbon divided by 12.01, its molar mass, gives us 0.94 moles of carbon. Now we're going to find the atom with the least amount of moles in the compound. In this case, it's carbon with 0.94 moles. We're going to divide all the moles of the atoms by the number of moles of carbon to get us the ratio of the atoms in the compound. 1.89 moles of sodium divided by 0.94 gives us roughly 2, so the ratio of sodium in the compound is around 2. 2.83 moles of oxygen divided by 0.94 moles gives us roughly 3 moles of oxygen, so the ratio of oxygen in the compound is 3. And finally, 0.94 moles of carbon divided by 0.94 gives us 1, so the ratio of carbon in the compound is roughly 1. And so, using these ratios, we get the formula Na2CO3.
Basically, if we're given percentages, we assume 100 grams, find the grams of each atom, convert it to moles, and divide each number of moles by the atom with the smallest number of moles.
You could also be given the amount of grams of the different elements in an unknown compound. For example, in this problem, a pure sample of an unknown compound has 10.8 grams of aluminum and 9.6 grams of oxygen. And the problem asks us to find the compound's empirical formula. Much like in the first problem, we're going to convert the amount of grams of each element into moles by dividing the grams of each element by their molar mass. 10.8 grams of aluminum divided by 26.98, its molar mass, gives us around 0.4. 9.6 grams of oxygen divided by 16 grams, its molar mass, gives us 0.6. Then we're going to find the element with the lowest number of moles. In this case, it's aluminum with 0.4 moles. We then divide all the number of moles by the number of moles of aluminum. 0.6 moles of oxygen divided by 0.4 gives us 1.5. So the ratio for oxygen is 1.5. 0.4 moles of aluminum divided by 0.4 gives us 1, so the ratio for aluminum is 1. Now you're probably ready to move on to the next problem, just like I am, but we're not done yet. Oxygen's value is still a decimal, so to get it to a whole number, we multiply 1.5 by 2, which gives us 3. We then have to multiply aluminum's ratio by this number, so we get 2. This means that the empirical formula of this compound is Al2O3.
To sum it all up, when you're given elements in grams, you convert the amount of grams to moles, and then divide every value by the lowest number of moles. If needed, you also need to multiply all the numbers by a single value in order to get a whole number.
Sometimes, after finding the empirical formula for a compound, a problem's going to ask you to write its molecular formula. Let's look at an example. This problem says that a compound has the empirical formula CH. 0.15 moles of this compound is 11.78 grams. And now the problem asks us to find the compound's molecular formula. First, we're going to find out the molar mass for the compound's molecular formula. 0.15 moles of the compound is 11.718 grams. So 0.15 times the compound's molar mass gives us 11.718 grams. We can divide 11.718 by 0.15 to give us 78.12 grams. Next, we find the molar mass of the empirical formula. The empirical formula here is CH, so it has 1 mole of carbon and 1 mole of hydrogen. We can take the molar mass of carbon, 12.01, and add it to the molar mass of hydrogen, 1.01. We don't have to multiply the molar masses of carbon and hydrogen by anything because their subscripts in this formula are just 1. 12.01 plus 1.01 gives us 13.02. Next, we divide the molar mass of the molecular formula by the molar mass of the empirical formula. 78.12 grams divided by 13.02 grams gives us 6. Now we're going to take this number, 6, and multiply it by all the subscripts in the empirical formula. So CH becomes C6H6, and that's our molecular formula.
In short, if you need to convert an empirical formula into a molecular formula, you find the molar mass of the molecular formula, divide it by the molar mass of the empirical formula, and multiply the value you get by all the subscripts in the empirical formula.
If you thought that was bad, now we're going to focus on finding the empirical formula of a hydrocarbon, meaning a molecule with just carbon and hydrogen, from a combustion reaction. And it's going to get tricky, so if you don't pay attention, your brain's going to combust.
If you didn't know, a combustion reaction occurs when a compound with hydrogen, carbon, and sometimes oxygen reacts with oxygen gas in order to make water and carbon dioxide. This usually happens when something's lit on fire or reacts with a lot of heat. The oxygen fuels the flame, and the burning of the hydrocarbon releases water as a gas and CO2. Some AP Chem problems will give you the amount of CO2 and H2O produced by a combustion reaction and ask you to find the empirical formula of the hydrocarbon reactant.
Let's take a look at an example. An unknown hydrocarbon reacted completely with O2 in a combustion reaction that created 5.28 grams of carbon dioxide and 2.88 grams of water. What is the empirical formula of the unknown hydrocarbon? Okay, first I'm going to give you an outline of the steps we're going to do and explain them. The products we know are CO2 and H2O, right?
Obviously, like, you'd be yapping about them.
Shut up, Steve. No one asked you. CO2 is the only product in this reaction that contains carbon, which means that all the carbon in our unknown hydrocarbon was converted to CO2.
This means that if we find the number of moles of carbon in the CO2 that was produced, we can find the ratio of carbon in the unknown compound.
Similarly, H2O is the only product in this reaction that has hydrogen. So all the hydrogen in our unknown compound was converted into the hydrogen in H2O.
If we find the moles of hydrogen produced in H2O, we can find the original ratio of hydrogen in the unknown compound.
So first, I'm going to start with finding the amount of moles of carbon from CO2. We're given the amount of CO2 in grams, which we need to convert to moles. The molar mass of carbon dioxide is 44.01, so we divide 5.28 by 44.01 to give us roughly 0.12. This is the number of moles of CO2. Since there is 1 mole of carbon in every 1 mole of CO2, we can assume that 0.12 moles of carbon dioxide gives us 0.12 moles of carbon. Next, let's figure out the amount of moles of hydrogen from H2O. We're given 2.88 grams of H2O. We divide that by the molar mass of H2O, which is 18.02, to give us the amount of moles of H2O. 2.88 divided by 18.02 gives us roughly 0.16 moles of H2O. In 1 mole of H2O, there are 2 moles of hydrogen. So we multiply that number by 2 to give us the amount of moles of hydrogen. 0.16 times 2 gives us 0.32, so we know that there's 0.32 moles of hydrogen. Next, we find the element with the lowest number of moles, which is carbon, and we divide both the number of moles that we got by the number of moles of carbon. 0.32 moles of hydrogen divided by 0.12 gives us 2.667, or roughly 2 2/3. 0.12 moles of carbon divided by 0.12 moles of carbon gives us 1. This gives us a ratio for hydrogen and carbon in this compound. However, the ratio for hydrogen is still this big ugly decimal that we need to convert to a whole number. The fraction form of the ratio is 8/3, which we can then multiply by 3 to give us 8. Since we multiplied the amount of hydrogen by 3, we also need to multiply the amount of carbon by 3. And 1 times 3 is 3. So we get our empirical formula of C3H8. If all of this seems really complicated, let me break it down in steps.
To find the empirical formula for a combustion reaction, you first need to find the moles of CO2 and H2O. From there, you'll find the moles of carbon and hydrogen. Divide both the moles of carbon and hydrogen by the element with the lowest number of moles, and convert the ratios you get for carbon and hydrogen into whole numbers.
Now we're going to be talking a little bit about isotopes.
While each element has its own unique number of protons, its number of neutrons can vary. Versions of the same element that have different numbers of neutrons are called isotopes.
Isotopes are usually written out by the element's name followed by its atomic mass. For example, carbon has the isotopes of carbon-12, carbon-13, and carbon-14. Now, you're probably wondering, how do you find the amount of neutrons in an isotope using the numbers at the end of its name? Well, the numbers at the end of an isotope's name give us the mass of a single atom of the isotope in AMU. An atom of carbon-12 has a mass of 12 AMU. The two particles that contribute to an atom's atomic mass are protons and neutrons. We know that every atom of carbon has 6 protons since that's its atomic number. So we can subtract the number of protons from the isotope's mass to get the number of neutrons. 12 minus 6 is 6, so every atom of carbon-12 has 6 neutrons. So we've talked about isotopes, and we've also talked about the average atomic mass on the periodic table. And now you're probably wondering, how do those numbers correlate?
If each element has all these versions of itself with different masses, how do we find the average atomic mass for each element that were shown on the periodic table?
Some AP Chem problems are going to give you the percent abundance for the different isotopes of a particular element.
Percent abundance shows you how often different isotopes occur in nature by giving the amount of each isotope as a percentage of all the isotopes of the element. The average atomic mass on the periodic table is found with these steps. First, convert the percent abundance of an isotope into a decimal. Second, multiply that value by the isotope's mass number. Third, repeat these steps for all the isotopes of an element. Finally, you add up all the values you get for the different isotopes.
Now let's try this method with the following problem. Carbon-12 has a percent abundance of 98.9%, while carbon-13 has a percent abundance of about 1.1%. Find the average atomic mass of carbon. Let's start with carbon-12. Converting 98.9 into a decimal gives us 0.989. Let's multiply that by carbon-12's mass, which is 12. 0.989 times 12 gives us about 11.87. Now let's do the same thing with carbon-13. Converting 1.1% into a decimal gives us 0.011. Carbon-13's mass is 13 AMU, so we multiply 0.011 by 13 to give us 0.143. Now we add the numbers that we got for carbon-12 and carbon-13. 11.87 plus 0.143 gives us 12.013, which we can round off to 12.01. So the average atomic mass for carbon is 12.01 grams. In this problem, notice how all the percent abundances for carbon add up to 100%. This 100% represents all the carbon in the world.
So if a problem asks you to find the percent abundance for a particular isotope, subtract the percent given for the other isotopes from 100, since the percent abundances for all the isotopes has to add up to 100.
We can also estimate an element's average atomic mass if we're given its mass spectrometry graph.
Mass spectrometry graphs give us the percent abundance for all of an element's different isotopes. Let's look at a mass spec graph from neon. As you can see, neon has 3 isotopes: neon 20, neon 21, and neon 22. Looking at the graph, we can see that neon 20 has the highest relative abundance at over 90%. And as we saw with our carbon calculations, the average atomic mass of an element is usually closest to the mass of its most abundant isotope. Carbon-12 had the highest percent abundance, and so carbon's average atomic mass was really close to 12. Here, although there are small amounts of neon 21 and neon 22, neon 20 is definitely the most abundant. So we can estimate that neon's average atomic mass is really close to 20, if slightly above 20, due to the small presence of neon 21 and neon 22, which have more mass than neon 20. And looking at the periodic table, we can see that the average atomic mass for neon is 20.18.
But what if these percent abundances are a bit harder to interpret?
The mass spec graph for palladium, PD, looks like this. There's relatively equal amounts of palladium 105, 106, and 108, and pretty small amounts of the rest of the isotopes. So we know that palladium's average atomic mass is going to be between 105 and 108. When comparing 105, 106, and 108's percent abundances, 106 seems to be the highest, even if it's not by much. So we can assume that palladium's average mass is around 106. But is its average atomic mass slightly above 106 or below it? If you're struggling with this type of calculation, add up the relative heights of the peaks around it. The combined heights of the peaks for isotopes heavier than 106 is slightly higher than the combined heights of the peaks below 106. So the average atomic mass of palladium is going to be slightly higher than 106. And if you look at the periodic table, the average mass of palladium is 106.42 grams. Because you can't magically move the bars around the screen on the AP test,
You should probably try to estimate the combined heights of the bars that are lower than or higher than the most abundant isotope. There should usually be enough of a difference between these estimates for you to pick an answer. So earlier in the video, we were going over this little topic called electron shells.
on the periodic table, the amount of shells an atom has increases with its period or horizontal row on the periodic table. For example, all the atoms in the first period have 1 electron shell, and all the atoms in the second period have 2 electron shells, and so on. For the atoms with more than one energy level, electrons need to fill up the previous energy levels before more electrons are added to the other shells. Each energy level has subshells that are filled up in an order. These subshells are called S, P, D, and F. The S subshell can hold 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold 10 electrons, and the F subshell can hold 14 electrons.
The first energy level has only one S sublevel, so it can only hold 2 electrons. We call those electrons 1s1 and 1s2. The 1 at the front gives us the energy shell they're in, the S gives us their sublevel, and the 1 or 2 at the end gives us the order in which they're added. Because the first energy level can only hold 2 electrons, the only atoms with one energy level are hydrogen, which has 1 proton, and helium, which has 2 protons. The atoms in the next period have both a full first energy level and a second energy level. The second energy level has an S sublevel and a P sublevel. The S sublevel is filled up first before the P sublevel is, so all the atoms after beryllium, which have 5 or more electrons, will start filling up their 2p orbital. In the third period, there's a 3s orbital and a 3p orbital, and much like the second period, the 3s orbital needs to be filled up before the 3p one is. And as always, the first and second energy levels have to be filled up before you can start adding electrons to the third energy level. Now, the next period is where things get weird. The order of sublevels filled up is 4s2, 3d10, 4p6. After the 4s sublevel is filled, electrons are put in the 3d sublevel, which is back on the third energy shell. The D sublevel can hold 10 electrons, and after the 4s and 3d sublevels, then the 4p sublevel is filled up. And as always, the p sublevel holds 6 electrons. The next period follows a similar pattern, with the sublevels going from 5s2, 4d10, 5p6. First filling up the 5s sublevel, then jumping back to fill up the 4d sublevel, then filling up 5p6.
In the next period, we fill up the 6s sublevel before jumping down to the 4s level. Yep, jumping back 2 energy levels. Then filling up the 5d, and then going on to 6p. In the last period, we fill up the 7s sublevel, jump down to the 5f, and finally fill up the 7p orbital.
So what exactly do you mean by like filling up orbitals? You just take an atom and like freaking just start like stuffing it with electrons like a sock monkey or something?
Huh. Well, I guess that's a good point. Why don't we take a look at an example? Arsenic. Arsenic has an atomic number of 33, so it has 33 protons. In a neutral atom of arsenic, we can assume it has 33 electrons too, since the charge of a neutral atom is 0. But arsenic's electrons can't just go in any random energy level in the atom. Its first 2 electrons have to go in the first energy level, so they fill up spots 1s1 and 1s2. Since the first energy level can only hold 2 electrons, we're gonna start adding electrons to arsenic's second energy level. First, we add 2 electrons to its 2s sublevel, filling up spots 2s1 and 2s2. Then we can add 6 electrons to its 2p sublevel, filling up spots 2p1 to 2p6. Electrons in the second energy level have to be added in that specific order, with the 2s sublevel being filled up before the 2p sublevel. Now, we jump on to the third energy level, putting 2 electrons in the 3s orbital, filling up electrons 3s1 and 3s2, and then adding electrons to the 3p orbital, from 3p1 to 3p6. But believe it or not, we're still not done. Arsenic's next 2 electrons have to go into the 4s sublevel. Next, we have to add 10 electrons to the 3d sublevel, which is the d sublevel on the third shell, so jumping back an energy shell. Finally, we have 3 electrons that haven't been added yet, and so we add them into the 4p orbital.
Oh, okay, I get it now.
Since each neutral atom has a certain number of electrons, we keep on adding that atom's electrons to fill up subshells in a certain order until we run out of electrons.
So like an atom like carbon, for example, it would put 2 electrons in its 1s subshell. Then it would fill up its 2s subshell and then like put the 2 remaining electrons in the 2p subshell, and then it would stop because it just ran out of electrons.
Well, that's right, Steve. In chemistry, we call this arrangement of an atom's shells and subshells its electron configuration. For atoms that have a bunch of electrons, that would take a really long time to write out completely. So because of this, sometimes we use a shortened electron configuration called noble gas configuration, or abbreviated electron configuration. We do this by writing out the symbol of the last noble gas that came before the element, and then writing out the element's additional electrons. For example, selenium, or Se, has a really long electron configuration when you write it out completely. Instead, we can first write out Ar in brackets, Ar for argon. Argon is the last noble gas to come before selenium, and its electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p6. So selenium basically has argon's electron configuration plus 4s2, 3d10, and 4p4. So instead of writing out the whole thing, we can abbreviate subshells 1s2 to 3p6 as Ar in brackets, and then write out 4s2, 3d10, 4p4. We can also write out electron configuration as orbital notation, which uses lines and arrows to show how electrons of an element occupy different shells. So for each sublevel, you write out its shell number and then the subshell's letter, such as 1s. Then, above it, you draw a horizontal line. This line represents an orbital, which are tiny parts of a subshell that can hold 2 electrons. P subshells will have 3 lines for 3 orbitals. S subshells will have 1 line for 1 orbital. D subshells will have 5 lines for 5 orbitals.
and F subshells will have 7 lines for 7 orbitals. So now that you've got all your orbitals and subshells laid out, it's time to draw in the electrons using arrows. For the filled up shells, each orbital will have two arrows, which represent 2 electrons. Draw 1 arrow facing up and 1 arrow facing down. This represents how 2 electrons in the same orbital will be spinning in opposite directions because electrons repel each other. For the sublevel that's not filled in, put 1 electron in each orbital before you start doubling them up and adding 2 electrons. You can also do an abbreviated orbital notation using noble gases. Alright, so let's do another example. Let's look at writing our abbreviated orbital notation for selenium, which has electrons in the 4p orbital. We can sum up the orbital notations for subshells 1s to 3p by just writing AR in brackets. That saves us a bit of time. Now for the 4s subshell, we first want to write out 4s. 4 for the energy level number, and S for the subshell number. We draw 1 line above 4s to represent 1 orbital. The 4s subshell for selenium is full, so we draw in 2 arrows representing electrons. One of the arrows is pointing up, the other one's pointing down. After 4s, selenium puts its orbitals in the 3d subshell, so we write out 3d. The 3d subshell holds 10 electrons, and since each orbital in a subshell holds 2 electrons, the d subshell has 5 orbitals. 5 times 2 is 10. The 3d subshell for selenium is completely full, so each of these orbitals gets 1 up arrow and 1 down arrow, much like the 4s subshell. Finally, the 4p subshell. Each p subshell holds 6 electrons, and each orbital in the subshell holds 2 electrons. So we draw 3 orbitals. Now, selenium's electron configuration ends with 4p4, meaning there's only 4 electrons in this sublevel. So we're going to have some empty space. We add 1 electron to each orbital before adding the last electron in as an arrow facing the opposite direction. Don't try to draw it like this, where you cram all 4 electrons into these 2 orbitals over here. So next, we're going to be taking a look at Coulombic forces and how they affect both electronegativity and atomic radius. So throughout this video, we've been talking a lot about how different electrons go into shells and subshells in atoms. And we've also been talking a lot about how, as you go down periods in the periodic table, the amount of shells that an atom has increases.
As the amount of shells increases, the distance from the atom's nucleus to its outermost shell, aka its atomic radius, increases. As this distance increases, the amount of attraction between the positively charged nucleus of an atom and its negatively charged valence electrons decreases. The forces of attraction between an atom's protons and its valence electrons is called Coulombic attraction.
For example, let's take a look at fluorine and bromine. Both atoms are in the same group, meaning they have the same number of valence electrons.
However, fluorine is in period 2, while bromine is in period 4. Because fluorine only has 2 energy levels, it has greater Coulombic attraction between its protons and electrons, because the protons and electrons are really close together.
I mean, fluorine's nucleus could basically grab those valence electrons if it wanted to.
Meanwhile, bromine has 4 energy levels since it's in the 4th period. This means that its valence electrons are pretty far away from the nucleus. Because of this, there are less Coulombic forces of attraction between bromine's electrons and its nucleus.
So the other factor affecting Coulombic attraction is effective nuclear charge. And when you're talking about effective nuclear charge, you're really only going to be comparing atoms that are in the same period, which means that they have the same number of energy levels.
So if 2 atoms are in the same period, atoms towards the right of the periodic table will have a greater number of protons, since their atomic number is increasing. This means that atoms towards the right of the table will have a more positive nucleus. This greater positive charge will attract the atom's valence electrons more strongly, creating greater Coulombic attraction. In addition, atoms with a higher effective nuclear charge will also have a smaller radius, as the strong positively charged nucleus will pull the electron shells closer to the nucleus.
So let's look at the differences between lithium and oxygen as an example. Both lithium and oxygen are in the second period, meaning they have two energy levels. Because of this, the amount of energy levels isn't really going to matter when we're comparing their Coulombic attraction. Lithium's atomic number is 3, so it has 3 protons in its nucleus. Oxygen's atomic number is 8, so it has 8 protons. Oxygen has more protons, so its nucleus has a stronger positive charge, aka a greater effective nuclear charge. This greater amount of charge means that oxygen attracts its valence electrons more strongly than lithium does, giving oxygen more Coulombic attraction.
When looking at the periodic table, we can see some trends with Coulombic attraction. Coulombic attraction increases as you go up the periodic table, since the amount of energy levels decreases. Coulombic attraction also increases as you go right on the periodic table, since effective nuclear charge increases. This means that atoms like fluorine, which are at the top right of the periodic table, have the strongest Coulombic attraction to their valence electrons. Meanwhile, atoms at the bottom left of the periodic table, like francium, have the least Coulombic attraction to their valence electrons.
So we've talked a little bit about the differences in atomic radius, but what about ionic radius?
Well, with ions that have the same electron configuration, the ion with the largest effective nuclear charge is going to have the smallest atomic radius. Likewise, the ion with the smallest effective nuclear charge will have the largest radius.
Okay, so right now you're probably confused, and this means it's time to look at an example. Now, the problem asks us, which of the following ions has the smallest ionic radius? S2-, Cl-, K+, or Ca2+. First, let's take a look at each atom's electron configuration. S2- has sulfur's electron configuration plus 2 electrons because of the net charge of 2-. This gives it the electron configuration of a neutral argon atom. Similarly, Cl- has Cl's electron configuration, but with an additional electron. This also gives it argon's neutral electron configuration. K+ has potassium's electron configuration, but with 1 electron removed, also giving it argon's configuration. Now you're probably starting to see a pattern.
Alright, wait a second.
What is it, Kevin?
If all these ions have like the same number of electrons and the same number of like electron shells, wouldn't they just have the same radius?
Okay, so here's the thing. Now that we know that all the ions have the same number of electrons and the same number of energy shells, we need to look at the other factor that affects atomic radius, which is effective nuclear charge.
Remember, the larger the effective nuclear charge, the stronger the Coulombic attractions between the nucleus and the electron shells. So, atoms with a high ENC are going to pull the electron shells closer to itself, decreasing atomic radius.
Among the 4 ions, Ca2+ has the highest ENC with 20 protons. Ca2+ has the strongest attraction between its nucleus and its electrons, so it has the smallest atomic radius. Now, another way to look at this problem is with the concept of electron shielding.
Electron shielding says that since electrons are negatively charged, an atom's electrons will repel each other, since particles with the same charges tend to repel each other. So, electrons on an inner energy level will slightly repel electrons on the outer energy level, pushing them away. This increases atomic radius. Positive ions that have electrons removed experience less electron shielding since they have less electrons. This decrease in electron shielding means that there are less repulsive forces between the electrons, increasing effective nuclear charge and decreasing atomic radius.
In this problem, this explains why the most positive ion, which is calcium 2+, has the smallest radius, because it has the least electron shielding.
This is also the reason why positive ions have a smaller atomic radius than their neutral atom counterparts. It's also the reason why negative ions have a larger atomic radius, because they have more electron shielding.
Okay, so now we're going to talk about the different factors that are affected by Coulombic attraction, specifically ionization energy.
Ionization energy is the energy required to remove an electron from an atom, starting with electrons on the outermost energy level. Different atoms will have different first ionization energy, or the energy required to remove the first electron from the outermost shell. This is due to Coulombic attraction. Atoms that have greater Coulombic attraction will have a higher first ionization energy than atoms with less Coulombic attraction. This is because greater Coulombic attraction means that there's a stronger attraction between the nucleus and electrons, so it takes more energy to break those attractions and remove the electron.
For example, fluorine's first ionization energy is 1,681 kilojoule per mole, with kilojoules being a unit of energy. Meanwhile, boron's first ionization energy is 800.6 kilojoules per mole, which is significantly less than fluorine's. This is because fluorine has greater Coulombic attractions between its nucleus and its outermost energy level. Even though boron and fluorine have the same number of energy levels, fluorine has a higher effective nuclear charge, which increases the attractive forces and slightly decreases the atomic radius.
But why do we start removing electrons from the outermost electron shell?
Well, electrons in the outermost energy level are farthest from the nucleus, which means that there are less attractive forces between the nucleus and the electrons. This makes it easier to remove an electron from the outermost energy level. If you remove more electrons, you would first remove all the electrons from the outermost energy level, and then remove all the electrons from the previous energy level, and so on.
So as you continue to remove these electrons, the ionization energy increases, because you remove electrons from shells that are closer to the nucleus. This concept of removing more than one electron from an atom is called successive ionization energy.
Ionization energy increases a little bit when you're removing different electrons from the same energy level. However, ionization energy increases drastically when you start removing electrons from another energy level that's closer to the nucleus. So let's look at an example. This is a chart of boron's successive ionization energy. You'll notice that there's a dramatic increase between the third and fourth ionization energy, as the ionization energy increases by 6 times. Let's look at why that is. Boron's electron configuration is 1s2, 2s2, 2p1. So it has 2 electrons in its first shell and 3 electrons in its second shell. When we start removing electrons from boron, we start with the electrons on the second shell since it's the outermost level. It's farthest from the nucleus and the electrons are easier to remove. In the first 3 ionization energies, we're removing 3 electrons from the outermost shell. And because those 3 electrons are on the same energy level, there's only a marginal increase in ionization energy. However, after removing those 3 electrons, there's no more electrons on boron's second energy level. So it's time to start removing electrons from the first one. Because of this, in boron's fourth ionization energy, we remove an electron from its first energy level. Because that first energy level is closer to the nucleus than the second one, the electrons on the first energy level have a much greater attraction to the nucleus. This makes it harder to remove an electron from the first energy level, so the ionization energy dramatically increases.
We can tell what group an atom on the periodic table is in based on its successive ionization energy. We do this by looking for a dramatic increase in ionization energy.
For example, in this problem, we've been given the ionization energy for an unknown element, and we need to find out what group it's in. The first 5 ionization energies increase from anywhere from a couple hundred to just over 1,000 kilojoules each time, so we see kind of a steady increase. But between the 5th and 6th ionization energy, there's a huge increase as we go from about 6,000 kilojoules to over 20,000. This indicates that between the 5th and 6th ionization energies, we've started removing electrons from an inner energy level, and we've jumped energy shells. So we're looking for an atom that has about 5 valence electrons, or 5 electrons on its outermost energy level. Because after that 5th electron, we've run out of electrons on the outermost energy level, and we've started removing electrons from an inner one.
Atoms with 5 valence electrons are found in group 15 on the periodic table. Because of this, we can assume that this is a group 15 element. And as we see here, the ionization energy chart was for phosphorus, which is a group 15 element. And finally, we're going to learn about photoelectron spectroscopy graphs, which show the amount of electrons an atom has, what subshells the electrons are in, and how strongly the electrons are bound to the nucleus.
PES graphs have binding energy on the x-axis and relative amount of electrons on the y-axis. On a PES graph for any atom, you'll see these peaks. Each peak represents a different subshell that an atom has, such as the 1s subshell, 2s subshell, 2p subshell, and you got the idea.
The peaks with the lowest binding energy represent subshells that are on the outermost energy levels of an atom, and the peaks with the highest binding energy are on the innermost energy levels of an atom.
This is because the closer an energy level is to the nucleus, the stronger the attractive forces are between the nucleus and that energy level. And the stronger these attractive forces, the higher the binding energy. The height of each peak shows how many electrons are in that subshell. For example, this 1s subshell has 2 electrons, and this 2p subshell has 6 electrons.
So based on an atom's PES graph, we can tell what element it is.
We can start by labeling the subshells. In this graph, the binding energy decreases as the x-axis goes on. This means that subshells with a higher binding energy are on the left, subshells with a lower binding energy are on the right. So we can start by counting our subshells from the left. The subshell with the highest binding energy is 1s, followed by 2s, 2p, 3s, and 3p. Now let's look at the height of our peaks. The 1s subshell has 2 electrons, the 2s subshell has 2 electrons, the 2p subshell has 6 electrons, 3s subshell has 2, and 3p subshell has 5. So this atom's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5, indicating that the element is chlorine. But what if this problem asked us to draw a PES graph for a different element, such as sulfur, based on this original graph?
Well, chlorine and sulfur have the same number of energy levels, but sulfur has less protons than chlorine, so it has a lower effective nuclear charge. Because of this, sulfur atoms have less Coulombic attraction between the nucleus and their surrounding electrons. That means that sulfur's electrons as a whole have less binding energy than chlorine's.
On this graph, binding energy decreases as you go to the right, so all the peaks for sulfur's graph would shift to the right. Sulfur only has 4 3p electrons, so its 3p peak would only show 4 electrons instead of 5.